Okay, for our final talk today in this session, productization and qualification of a 22 Newton bipropellant hydrogen peroxide engine, and that will be by Mr. Thomas White of Benchmark Space Systems.
So, when I was in college, I thought that the reason why propulsion wasn't easy was that there weren't enough people thinking about the things in Chapter 3 of Rocket Propulsion Elements by Sudden. And if we just had enough people do that and really think about the Bart's equation and the Lev-Lev correlation and the coefficient of thrust and come up with some cool thing, then we would solve all our problems. What I've learned in the propulsion industry, the actual answer is, what people need in order to accomplish their mission on orbit is propulsion that they don't have to worry about. Propulsion where they don't have to go to a conference presentation and learn about the technical specs so that they can feel confident. Propulsion that just works. That's why we don't always talk about that enough. That's why I'm so excited to talk about the productization of the 22 Newton green bipropellant engine, Ocelot, that Benchmark Space Systems provides. So, Benchmark, we've been around for 8 years. We make a whole variety of electric and chemical propulsion systems. There's so much to talk about, and you can hear all about it in booth 700, where we have the rest of our content. But today, I am going to talk a little bit about us, and then mostly about our Ocelot engine. And you can consider this kind of a sequel to the presentation we did at 3AF in the UK, if you were there. We do all kinds of different stuff. We do electric propulsion systems, we do chemical propulsion systems, we do ascent propellants and hydrogen peroxide propellants. We are, though, beyond that, your mission assurance partner. So that means we are involved from the very beginning. We do your initial sizing, if that's something you need help with. We are there to load propellant on your spacecraft. We work nights and weekends if there's something strange on orbit and you need help. And that all goes back to making it just work and not be worried about. Today, I'm here to talk about Ocelot. So Ocelots are 22 Newton hydrogen peroxide octane bipropellant engine. It's a full-flow catalyst bed on the hydrogen peroxide, and you post-inject the fuel, which means you can do a bunch of cool operating modes. You can fire it in biprop for high efficiency, monoprop for tiny pulses, or even crazy stuff like just pulsing the fuel. And we've gone through 3 different iterations. The very first one, Ocelot 1.0, was a demonstration protocol model. We flew it, did a 700-kilometer orbit raise, helped out the customer, did great, but just getting started. The next one, 1.1, was our first fully qualified article, which we built a production run of and helped support, among other things, the exploration company's Mission Possible mission that flew recently. 1.2 is the one I'm here to talk about today. That's the productized version. The version where we say, okay, now we understand what the customers want. Let's make sure that they have all of it. Ocelot 1.2 has been productized. It's been qualified comprehensively. We've shipped 30 of them, 5 are in space right now, and 34 more are under contract for multiple customers, one of which I'm very excited to finally be able to talk about is Varda Space Industries. And today, I'm going to talk a little bit about development and then mostly the fun stuff, in my opinion. So development, this is the part that we all talk about in these sorts of conferences from the very beginning. This is the part where you learn about ISP and you try all your different cat beds and you do your different injectors and all of that. And Benchmark is very good at that. In our California facility, we can do a fully new part number engine twice a week with in-house manufacturing capabilities and test capabilities. If you want to hear more about that kind of stuff, our Macaw engine right now, we did 34 different engine iterations in 2.5 months. Come talk to us at booth 700. But that's not the part I'm here to talk about on Ocelot. We did that back in the day. Today, we're here to talk about qualification and productization. First off, qualification. So Benchmark has an in-house standard, 10.07.29, which is built off of SMCSO 16 and 25 and JEBs and all the good stuff that we're all familiar with for environmental and qualification testing. We have all this stuff in-house, so we can do our TVAC and your vibe, everything that you need on the functionals, and we can do all of your hot fire. One of Benchmark's core values is extremely high cadence and volume testing, which is enabled by non-toxic propellants. Especially with hydrogen peroxide, one of the cool things is you can fire this thing with essentially none of the logistics operations that you need for really hazardous propellants like stuff that contains hydrazine. So in our facility in Pleasanton, we can complete an entire hot fire from test readiness review to propellant loading, to hot fire ops, to data upload and processing in 3 hours, which means that often we can have lunch, hot fire after lunch, and get some data in before it's time to go home for the day. This year, we fired various Ocelots for 20,000 seconds, tested over 50 serial numbers, take 12 of those engines and tested them to destruction, which is my favorite part, and can do up to 500-second continuous burns. And when our customer needed it, we can hot fire the next day. So qualification was a lot of hot fire. We did repeatability. These are the pressure curves for a whole bunch of different operating modes at the very beginning of one of the thrusters live and at the 2x endpoint. So after we fired it for twice what its qualified life is supposed to be, to demonstrate that the same thruster has good burn-to-burn variability and doesn't degenerate even as the CAPA gets a lot of time on it. We ran PCMR. Unlike some other folks, we do 10% operational qual box. And as we'll talk about later, it can go beyond that as well. It's a cool part of the architecture. We had a lot of impulse bit improvements on the 1.2 as we optimized the packaging upstream. So here's the 1.1 to 1.2 comparison to show how much is possible there. And we finally ran a full spectrum of minimum impulse bits. So with the monopropellant mode on this, we can get all the way down to 0.06 Newton seconds on a 22 Newton thruster. Finally, and what the cool thing about this Peroxide octane architecture is we can do a bunch of different fun stuff with the operating modes. Like I said, there's biprop and monoprop. You can pulse just the fuel. You can run at crazy high mixture ratios. And because the propellants are decoupled, the instability modes don't actually phase across, which is really neat. We are tested with a couple seconds of bubbles on various propellants and hard starts. This one is a great example. We induced a hard start deliberately. And despite the fact that we ran at twice the nominal chamber pressure for a hot sec there, we then evened out and completed the rest of the burn nominally. But let's talk about productization. This is the part I'm excited about. First part came when it was baked in the design. Talked to a lot of customers and hear what they want. So if you want different feed systems, we have tunable orifices on the top, and we'll give you whatever inlet pressure that you need. If you're worried about FOD, we have 2 sets of built-in last chance filters, including one directly above the injector and one directly up the valve. If you want to have an extra heater on the valves for better thermal control, or if you want to attach a MLI blanket, we've got optional add-ons. If you want to save 30 grams, you can take those off. That kind of stuff starts off in the design. But beyond that, the moment we finish qual, we keep testing. On the environmentals, at one engine, we took to 8 times the qual lifetime, which was already decibel loads over what we'd previously done. Then it passed acceptance. We qualified vibration facing up, facing sideways, facing down, customer-specific mode shapes. In the TVAC, people ask, like, hey, how long does the preheat take? Our answer is, depends on how much power you want to put into this thing. If you want it to happen in 20 minutes, it can happen in 20 minutes. If you want it to happen in 5 minutes, put more power in it, you can have it in 5 minutes. We took it to a TVAC and kept putting more power into it till it breaks, and then we can go put that in our user manual and tell the customers, we know the maximum amount you can put into this thing safely. We took units to qual life duration. We took some more units because when you pulse in qual, right, you can't see full thermal life. We then took units into just continuous life duration. We have over 50 acceptance test records, so we can do real Silicon Valley big data on these engines now. And when customers needed help, because for some reason they've got something going on, we supported expanded qual bounds on a day or a week turn time. So for example, when a customer said, oh my gosh, we need plus 20% chamber pressure, we went and did that. They said we need to run down to 88% hydrogen peroxide. We went and did that. We had one customer, this is my favorite one, honestly, who said that they needed to check whether or not the chamber could go down to negative 190 Celsius. I can't say and don't really want to say why they thought that was a relevant case, but we tested it and it can. Finally, we went back into the production and really nailed down every single bit. I look at that thruster right there. I have opinions on what style of knot are used on the harnessing because we tried 3 or 4 different kinds, and there's one of them that is both faster to manufacture and less likely to come undone during handling. We rejiggered the way that the weld operations move and our part designs in a way that allows us to go from order to inventory on some of our advanced refractories in 3 months, and then from inventory to acceptance test in 3 weeks, and produce a thruster out of the facility every single day. All right, that's all sunshine and roses. But truth is, the reason why we're all doing this is make propulsion you don't have to worry about. The only way to know whether or not you have to worry about it is to find out when there are problems. So when we talk about that hot fire capability, a lot of it is running tests that you think are going to succeed and seeing that they do, but some of it is to find out what can break and then fix it as fast as the customer needs. So today, I get to show you guys a picture that I normally don't get to show people. I'll set the scene. It's me. I'm on console. Some of the other California prop dev team members are operating the rest of the hot fire setup. We're in the middle of qualification on 1.2. And we see that. It's a propulsion engineer. I don't like that. That's stuff coming out of the wrong part of the nozzle. What's actually happening there, as we very quickly were able to identify as we pulled the thruster off, is that we've got a refractory alloy with an oxidation coating. That's an oxidation coating failure followed by rapid burn through of the alloy. Now, this was weird because this engine had failed well before the nominal qualification lifetimes of these engines. We had done a bunch of them. We knew how long they lasted. This was way early. So we got to work. Thing number one, that same day, after an hour of thinking, we pulled that thruster off the stand, put a different thruster on the stand, and fired the same propellant load on the same thruster to check, okay, could it be the propellant? Could it be the stand? Is there something weird operating here? Did fine. Okay, well, it's not that. We pulled a whole bunch of different thrusters using the same material system, but with different internal design elements. Fired them, they did fine. Okay, it's not that. Could it be the operating mode? We pulled another thruster and ran PCMRs and pulse conditions and a whole bunch of different replications and slight exceedances in different directions on what we've been testing. Well, that didn't cause the problem. Okay, next step. We looked at, could it be that it actually was hotter and our thermal measurements were all off? We ran a requal program on our thermal measurement systems, starting with Thomas with a blowtorch and working its way all the way up to some very nice testing. Now thermal seems good. Okay, could it be that something weird is on this thruster itself? We pulled the thruster, chopped it on the lathe, got the fuel and aux injectors, and then did a flow through, like a cold flow on them, and verified that they had good injector performance, atomization, nothing was off axis. We pulled the chamber, XRM, SDS, the whole deal, to try to see if there's some chemistry that we weren't understanding that was unique to the material system that we'd worked on. Nope, looks fine. Finally, we said, okay, we've been eliminating all those other things, gotta be a stochastic issue. We pulled the rest of the chambers in that batch and started hot firing more, and that was the ticket. As we fired them, we discovered that these guys were failing, and they were failing on, in a stochastic form at various different times and temperatures. That was the secret. Now we knew where to look. So on the inside of the chamber, you can do, and we do all kinds of acceptance test measurements, including surface profile, but you can't get surface profile in very small parts in the throat. So that is manufacturing process dependent. Cut the chambers, ran a profilometer on the inside, discovered surface roughness variation on just one particular part of the throat that wasn't enough to show up in the previous acceptance testing, but was enough to slightly change the distribution in the heat treatment process of the coating that we put to prevent the refractory from oxidizing. With the slightly different distribution pattern on the inside there, combined with very slight projections that caused local heating that didn't show up on the exterior thermal cameras, you had variations in coating thickness, which caused variations in thermal lifetime. We fixed the problem with the printer, and I have made sure that that didn't reoccur. Added 2 more processes to add the extra surface roughness and assure that that will never come up again. Understood the physical geometry, built a CFD model, proved that the CFD model showed failure temperatures at the location with the coating behavior that we understand if we were able to perturb off of the original measurements that we pulled from the profilometer. Took the engines, ran the rest of the qual program in 2 months, and then had customer shipment a couple weeks after that. And then, and the most fun part of it, we had a batch of engines that we knew we couldn't fly because they are bad, and we took all of them to life. And in doing so, we're able to prove out a little bit more about our cap heads, a little bit more about the rest of our engines, and material data on extreme high life testing of a niobium coating system that basically doesn't exist, because if you look at all of the niobium coating systems, no one would be crazy enough to run their engines at above failure temperature for this long, except us. So the lesson learned here is not that we make engines which are going to be perfect the first time. No one's engines will be perfect the first time. But what we can say is that we build engines where all of the imperfections happen in Pleasanton, California, and are understood and solved so that by the time that you have it on your spacecraft, you don't have to worry about it. Thanks very much.
Thank you, Thomas.